Hi guys, welcome to our channel JEE Foundation. In our channel, we introduce tricky problems and ways on how to solve them that improve conceptual understanding and problem solving skills which are required to crack JEE and other competitive exams. Today's topic is surds, in which we'll be solving for the value of a nested root expression that has finite number of nested roots. On our previous video, we solved for the value of infinite nested roots, so please go check out that video as well. For example, we'll be considering mth root of 7 multiplied by 7 whole mth root multiplied by 7 whole under mth root repeated n number of times. Instead of infinite nesting of radicals, the expression has n nested radicals. Thus, the simplification used for infinitely nested radicals of the previous video, that is infinity minus 1 is equal to infinity, cannot be used here. But the value can be found by removing one mth root at a time and repeating it n times. Let x equal to mth root of 7 multiplied by whole mth root multiplied by 7 whole under mth root repeated n number of times. Thus, raising both sides of equation 1.1 to the mth power, we get x to the power m is equal to 7 multiplied by mth root of 7 multiplied by whole mth root of 7 multiplied by 7 whole under mth root repeated n minus 1 number of times. As a result, it can be seen from the right hand side of equation 1.2. The outermost radical is removed and that 7 has come out and the radical part now has n minus 1 nested radicals. Raising both sides of equation 1.2 to the mth power, we get equation 1.3, which is x to the power m is equal to x to the power m square, which is equal to 7 to the power m multiplied by 7 multiplied by mth root of 7 multiplied by 7 whole mth root multiplied by 7 whole under mth root repeated n minus 2 number of times. As a result, the 7 outside the radical is raised to the power m and the outermost radical is removed, moving another 7 out of radical. We can write it as xm square is equal to 7 to the power m plus 1 multiplied by mth root of 7 multiplied by 7 whole mth root multiplied by 7 whole under mth root repeated n minus 2 number of times. Raising both sides of equation 1.4 to the mth power, we get x to the power m square to the power m is equal to x to the power m cube, which is equal to 7 to the power m plus 1 to the power m multiplied by 7 multiplied by mth root of 7 multiplied by 7 whole mth root multiplied by 7 whole under mth root repeated n minus 3 number of times. As a result, the 7m plus 1 outside the radical in equation 1.4 is raised to the m power m and the outermost radical is removed, moving another 7 out of radical. We can write it as xm cube is equal to 7 to the power m square plus m plus 1 multiplied by mth root of 7 multiplied by 7 whole mth root multiplied by 7 whole under mth root repeated n minus 3 number of times. We summarize the 3 steps by looking at how the power, that is index of x, on the left hand side and 7 on the right hand side grow each time the expression is raised to the mth power. We can see the number of times expression raised to mth power in column 1 and the corresponding powers of x and the leading 7 in the second and third columns. In equation 1.2, the expression was raised to the mth power once. Thus, the index of x was m and that of the leading 7 was 1. In equation 1.4, the expression was raised to the mth power twice. Thus, the index of x was m square and that of the leading 7 was m plus 1. In equation 1.6, the expression was raised to the mth power thrice. Thus, the index of x was m cube and that of the leading 7 was m square plus m plus 1. Using the above table, we find a pattern for the growth of index of x and 7. If the expression is raised to the mth power p times, then the index of x is m to the power p. If the expression is raised to the mth power p times, then the index of 7 becomes a series sum, which is m to the power p minus 1 plus m to the power p minus 2, which goes on till 1. Next, we simplify the above series. Also, it is important to note that this is a series sum and not strictly part of surds. This sometimes happens for problems that involve methods of two different chapters, and many a times we may not have done the second chapter. Let S be the sum of the series. Multiplying both sides of equation 1.7 with m, we get ms is equal to m to the power p plus m to the power p minus 1, and it goes on till m. Subtracting equation 1.7 from equation 1.8, we get m minus 1 whole into s is equal to m to the power p minus 1. Or we can write it as s is equal to m to the power p minus 1 by m minus 1. Thus, we find that on taking mth power of the surd p times, we get x to the power m to the power p equals to 7 to the power m to the power p minus 1 by m minus 1 multiplied by mth root of 7 multiplied by 7 whole mth root multiplied by 7 whole under mth root, repeated n minus p number of times. Therefore, opening all radicals, that is taking mth power of the surd n times, we get x to the power m to the power n is equal to 7 to the power m to the power n minus 1 by m minus 1, or x is equal to 7 to the power m to the power n minus 1 by m minus 1 whole into m to the power n. Thus, the answer to the mth root of 7 multiplied by whole mth root multiplied by whole 7 whole under mth root repeated n number of times is equal to 7 to the power m to the power n minus 1 by m minus 1 whole multiplied by m to the power n. In general, if r is any number, then the mth root of r multiplied by r whole mth root multiplied by r whole under mth root repeated n number of times is equal to r to the power m to the power n minus 1 by m minus 1 whole multiplied by m to the power n. In the above expression, if m is equal to 2, then the root of r multiplied by r whole under root multiplied by r whole under root repeated n number of times is equal to r to the power 2 to the power n minus 1 by 2 to the power n. To summarize what we have learned, we can say that the problem required the following inputs. The first one is repeatedly opening the outermost radical by taking the mth power of the expression. Second, finding a pattern in the growth of the indices on taking successive mth power. And third, ability to express the pattern in general terms, that is, if the mth power is raised p times, then what is the indice value in terms of p? An important thing to note is the indices pattern involved in finding sum of a series is not part of the methods introduced in surds chapter, but is a part of the sequence and series chapter. For many students starting out on solving problems, it may appear sometimes that problems are tough since they could not figure out how to sum the series. They should not worry about such things, but be aware that the solution involves something not introduced in the current chapter, and make a note of such things for future reference. So, thank you guys, that's it for today, and thank you so much for watching our video. If you enjoyed our content, then please subscribe to our channel and hit the bell icon. And also, please like our video. This helps the YouTube algorithm promote our learning content so that others can access it as well and benefit from it. Bye. See you in the next video.